Hey, welcome back, everybody. Today we're going to continue our AP review series for this year. And last time we were talking about integration, some basics, what it meant graphically, and then ways that we can approximate it using different areas. And today we're going to look at really an important concept, clearly by the name, the fundamental theorem of calculus. And I want to begin with our first idea. And remember, the fundamental theorem of calculus really bridged the gap between differential calc and integral calc. So I'm going to begin this by looking at the idea of defining a function as an integral of some other function. So let's say we let g of x be equal to the integral from a to x of f of t dt. If we were to take the derivative of this function g, this would simply get rid of our integral and we'd be left with f of x. Now, this is a pretty simple concept. We spent time talking about why this was true in class, but really my goal here today is just to refresh your memory of it. Now, just to do a quick example problem with this, let's say that you were asked to take the derivative of the integral from x squared to 3 of the square root of t cubed plus 1 dt. So if we were to take the derivative of this integral function, now this one, the x term is in the denominator, so in order to get it up to the top, we're going to negate and switch. Remember, the number here, 3, does not matter. So this is going to be negated first. The integral will go away. X squared will plug in for t, so that'll give us x to the 6th plus 1. And then we're going to apply the chain rule. We're going to multiply by the derivative of the piece that we just put in, so 2x. So that would be the derivative of this integral function. Very, very simple problem, and something we want to make sure that you can do relatively easily. You're given an integral function and asked to take the derivative of it. It's that simple. Okay, now let's get into probably the most important concept in integral calculus. And that's the idea of the integral from a to b of a function f of x dx and what it is equal to. Remember that an integral represents the net area under the curve, and now we're going to change that and kind of expand that understanding and that knowledge. And we should know from class the way that we evaluate an integral like this is to first take the antiderivative, which would be, in this case, would be big F of x from a to b, which is equal to f of b, big F of b minus big F of a. So the definite integral from a to b is equal to the net change in value of the antiderivative. The net change in value of the antiderivative. Over the interval from point A to point B. So the net change in the antiderivative of your integrand over that interval. That's all it is. The applications of this are huge. We're going to get to that in a later lesson, but you can probably already start to refresh memory on what some of those applications might be. Now, I do have an alternate version of this that I always like to share. And that alternate version makes a simple modification. Oftentimes, this concept is used to figure out a value of something based on some known point that you're given. And then I call this my modified version of the FTC. What if I take this big F of A and I add it over to the other side? Now I've created a new expression that could be used to find the value of big F of B if I were to know the value of big F of A. So if I were given some point and then I calculate the net change from that point to my new point, I'm going to determine the value of my new point. A lot of different ways that this could look. Maybe it deals with f of a, and now my integral is involving f prime. This gets asked all the time on problems involving the f prime graph. Figure out some new value of f of x based on some given value of f of x. The value of f plus the change in f from a to b is the new value of f. And obviously, we're going to extend this to particle motion. Integral is net change involving rates of change, and a whole bunch of other stuff that's to come. And at this point, guys, I'd also think it might be a good time to remind you that reviewing your antiderivative rules, make sure you have everything down. We'll do a lot of work. We'll have a whole nother lesson dedicated to advanced integration techniques. But your other antiderivatives you should know pretty well. And don't focus too much on memorization. Focus more on working back from the derivative rules that you know and going backwards. But definitely review some of the key ones so that you're ready to go. We won't spend too much time talking about here. I'm focused more on the concepts and getting you ready for those. All right, third part. This is not part of the FTC, but I just want to make a little plug for it. Remember, indefinite integral is simply asking you to just take the antiderivative and then plus the constant of integration plus c. No values to approximate. So that's a little bit of a side topic, but I thought it was a good time to plug that in and remind you again, make sure you're ready to go for all of your basic antiderivatives. Okay, the last thing to look at today, and I think the graphs are going to be important. There's a graph problem that comes up in this section that is very common on the AP exam. So let's say that you know a function g of x is equal to the integral from 0 to x of f of g. So we define an integral function g. And then a problem gives you the graph of f. So I'm going to create a nice looking sketch here. Three, four. I'm going to create a graph that involves a semicircle of radius 2, a rectangle underneath it, a line coming down this way, and extending through to here. That is a rough sketch. That's okay. You get the idea. So let's say this is the graph of f. And if we define g as the integral of f, we can work with this pretty easily in answering several different questions. The first thing I want to look at is evaluating g. Let's say I ask you for g of 8. Think about what we would look at on this graph to determine the value of g of 8. If g is the integral of f, then this would be the integral from 0 to 8 of f of t dt. We would take the time, we'd find the area of each of these shapes. So if I start first, we have a rectangle. That rectangle is 4 by 2, so that's an area of 8. The semicircle is equal to 1/2 times pi r squared, and the radius is 2. And then I have these two triangles. This triangle here would be added, and this congruent triangle would be subtracted. So they're going to knock each other out, so I'm not going to include that. So my area from 0 to 8 would be equal to 8 plus 2 pi. Okay, another thing that's unique is we might have to maybe find g prime of 8. Well, if I go back up to here and take the derivative of g, this would just be equal to f of x. So this is just going to be f of 8, which is the point at 8. So if I go out to 8 right here, what is the y value at that point? It looks like it is -2. A third thing maybe is g double prime of 8. If I were to take the derivative of g prime, which is f, this would just be equal to f prime of 8. And let's do a different point. Let's switch it up. Let's do an interesting point this time. Let's make it g double prime of 4, and then f prime of 4. Well, if this is the graph of f, f prime would be the slope at that point. So if I go to 4 and I look at the slope, I have a cusp. So this is going to be non-existent. The slope doesn't exist at that point. Now, other questions that could be asked here, there could be anything about the behavior of g. And I'm not going to spend time going through all of these. Maybe I ask you, when is G increasing? Well, if f is equal to g prime, interpreting this is the same as interpreting the derivative graphs from the previous section when we did f prime graphs. So I would look at anywhere f is positive, so from 0 to 6. And any other problems of this type, when I answer questions about g, I would read it the same way that I read a derivative graph. If I was asked where is g concave up, that would be from 0 to 2, right, where it's increasing. G has a local maximum at x equals 6 because it's changing, f is changing from positive to negative. So once this relationship is established, this problem is pretty straightforward from there. You might see other things involving, max and min and things like that, but those are all things that I think you can apply your previous knowledge to with this new knowledge and be able to figure out. Okay. All right, that is it for today. And please reach out if you guys have any questions about anything else. Thanks for watching.